Joe is a senior software engineer working on Coinbase's ML platform. You studied at Cornell and previously worked at Microsoft and founded and exited Root Storage. Over to you.
Perfect. Yeah. So thanks, Jim. I'll be talking about sequence features at Coinbase. I work on our ML platform team here, and we do all of our training, serving, infrastructure, and framework layer on top. And just a quick agenda. I'll give a brief overview of why Coinbase has invested in an ML platform, our core predictive ML use cases, and a bit of the scale that we have. And then I'll jump into the core topic, which is going to be a mix of both our streaming pipelines and work we've been doing to make it really easy to build streaming features at Coinbase, and then also specific aspects and how they relate for the purpose of sequence features and sequence learning. And I'll just wrap up with some of the ongoing work in areas where we're trying to improve things. Cool. So if you look at different applications that leverage our feature platform, we have a few core predictive ML use cases. The reason the team was formed in the first place was for fraud detection to protect our customers in Coinbase. And then we also have a lot of recommendation systems internally, customer support chatbots, and compliance use cases. And I think something that's pretty common, I imagine, for other fintech companies is we have a lot of decision engines. So they're not actually like a machine learning model that's consuming the features, but you might be creating rule-based decisions based on features. And so like different rules to power risk decisions. And then we also have some even non-decision engine use cases where feature store can be used for very specific use cases for this reverse ETL and online data serving, where you have long-running streaming aggregation and you're grouping by a specific entity and doing some aggregates. We do find some users come to us for that as well, although there are other options at Coinbase on the data platform side too. And to give you an idea about the scale, we have around 100 internal feature platform users, and there's a very wide range of personas, machine learning engineers building models and these features, common one, but then also we have analysts who maybe have a lot less streaming experience, but a lot of domain expertise with risk modeling and risk features. And then also data scientists and software engineers. So it's a very diverse persona, and that's going to inform a lot of the work I'll talk about later is how do we make it easy for all of these different personas to build high quality streaming features. And then we have over 30 different use cases like in production for online feature serving. And it's a little bit out of date now. We're actually over 10,000 features internally. And the big piece too, related to some of the work here, we've had a major increase in the number of streaming workloads where streaming now can become the default, especially for latency sensitive fraud and recommendation systems use cases. So we've over 2x increased the number of streaming workloads in just the last 12 months. This is actually from last week's crypto volatility, reached a new peak, which was 500,000 online reads per second for online features. Cool. And then the kind of core topic we're going to be talking about is sequence features. And so when we look at traditional feature engineering, we're typically doing rolling window aggregates, which we've talked a ton about. Like you might create a feature, if you look at this data set, that's like how many times has the user signed in the last 1 month or last 1 day. Or you might even do just like the sum of transaction volume. These would be classic features. We have a ton of those. That's the majority of those 10,000 features I mentioned earlier. But then you could also view this differently and instead try to model the interactions as sequential. So in this, we could also view this as a user signed in, then they sold an asset, then they bought an asset. And we can try to use those sequential data directly in our models. And so that's kind of the core purpose, is to talk about some of the differences and how we're trying to make it really easy to do this type of feature engineering. And so if we want to talk first about like what would be potential motivation for this? And so I think the intuition here is that when we look at a rolling window aggregate, it's kind of inherently a lossy aggregation. You're taking a bunch of data and you're compressing it down into a single aggregate for like a very specific time window, 30 days, 1 day, 7 days, lifetime. So you might be reducing useful information. And then also, while you are like selecting time ranges, and these are all point in time features, you're not directly modeling on the temporal and sequential nature of the data. And so those are two reasons we might think to look for sequence features to see if we can improve model performance. And then the two ways that we use this a lot right now, the first one is that these sequence features can be used to generate very generic embeddings that we can use for lots of different models. So you might try to use sequences of user interactions to generate a user embedding or an asset embedding for Coinbase. And then you can use those as features for many other recommendation system models. So you get like a very generic representation and you don't have to go engineer many different features, many different traditional features. And the other one, it's super common and it's very different profile for these workloads is that when you're trying to make a fraud detection prediction in real time, you may choose to also incorporate sequence features directly into your model alongside traditional features. So we have many deep learning models at Coinbase, and you can actually just add separate blocks to a highway network to use a transformer, for example, and just use that alongside a traditional feature. So it's another way that we use this widely. And so before we dive into some of the work we've done, I just want to like kind of set the stage for some of the core constraints we look at when we're talking about sequence features. So first is like what events do you want to actually consider when you're building a sequence? And so we find it's typically less than 100, but often like less than 10, a small number of core events related to really critical user activities on Coinbase. And then sequence length, I think up to 1,000 events at a given point in time prediction is kind of where we typically work with, although you can do offset windows. So you might say, I want the 1,000 most recent things the user did, and then also maybe offset by a day to get the most recent 1,000 things a user did in the previous sessions, not the current set of events. And then also the look back window is super dependent, kind of what I was getting to. Some cases we really just want to look at the last hours or even minutes of activity. Other ones we want to look at lifetime sequences, as much data as we can get for the user. And freshness, again, is like widely different for a Rexus use case. It might be just batch predicting embeddings daily. But then for risk, we're often in sub-second and measuring things in milliseconds for freshness of the features. And offline read time latency is kind of a core constraint here where MLEs will always want faster training data generation, and sequence features can be quite complex to compute. And so we kind of want to try to keep this as fast as possible. Typically, we want to go for less than 1 hour if we can, but we're trying to keep it uh, less than a few hours so that you can generate new training data really quickly as you're iterating with many different types of features and adding new ones to the model. And last one is online read time latency is can be very strict requirements, especially for things that are on the hot path for user activity. So we're looking consistently at less than 100 milliseconds for many models, where some are also a little bit less restrictive with their requirements. Cool. And so I'm just going to zoom out really quickly to like focus on what the area we're going to be talking about. So Coinbase, we have a ton of Kafka events across the company in many different topics. We've also Delta Lake tables with the data that's backfilled uh, of the Kafka events. And kind of where the work of the feature platform comes in is to handle computing features based on those different sources and letting users define their business logic and do a feature view transformation. And then, similar to all the other presentations, we handle the rights to the online offline store and ensure there's strong consistency guarantees. And so what we want to do, and some of the work we've been doing, is to try to make it as easy as possible to incorporate new events into your models and to generate sequence features or just traditional streaming features in a way that feels as easy as writing a batch feature. And so obviously there is more complexity though, because we're looking at multiple different events and we have different streaming and batch pipelines we're orchestrating. And so just to look at the user experience of what we built, the first is we explicitly declare the events that are going to be used in ML models. And you can add new ones as an MLE very quickly. You just need to declare name, version, schema. You add some other metadata. And we now have the schema for the fields that you're intending to use. And then we can version this as things change with those events. And so we have like many, many dozens of events now that have been registered here. And what this lets you do once they're registered, and assuming you're just selecting some existing events that another engineer already registered previously, is you have a single line of code and you can select any number of events. You just pass in the array of the events that you're interested in. Here we're saying, give me a data source that's going to have sign-ins and buy events only, and we'll give it a name. And then under the hood, we're actually going to be able to union multiple different Kafka topics, unify the schema. So there's some logic here to handle if the events have the same field with a different type, we'll take the wider of those two types and we'll generate a data source that you can then use that's going to just have a standard user ID, event name, timestamp, and metadata. Of course, if we're using a different, you can also pass in an entity and say, okay, we're going to be aggregating based on the asset ID instead of the user ID. And we'll also handle unioning multiple different Delta tables. So if you have those different topics, we'll have different offline event tables. That's also abstracted away. And our goal here is just to make it so that if you try sign-ins and buys, and then you're doing some data exploration and you realize there's another key event that you want to include, you can just add that, create a new source, and everything else in your SQL can be very similar. So that's kind of one of the first pieces, encouraging reuse. And then the actual computation of the features is very similar, but where for normal streaming features. But where we also have a lot more use cases is on these derived features. Like this example on the left is some real code that we have, and it's pretty trivial, but what we're doing here is taking a sequence of events and the timestamps, and we will insert a special token, in this case, like that day token you're seeing, to hit to the sequence. So now we're adding those so that the model can easily learn for this task to differentiate between the different days. And there's tons of other examples of this. You can interleave multiple different sequences with this approach. You can compute the entropy of a sequence, like one of these arrays. And so we have a bunch of these different UDFs defined, and then you can plug and play, select which ones you want. And yeah, these are Python UDFs that'll run in real time or in Spark as a UDF at training data generation time. And so one thing I want to talk about too here is what I think is a pretty interesting optimization. We're talking a lot about different approaches for tiling and like windowed aggregates. Like a lot of the previous presentations, like the key thing that's really critical here is that when you're doing a traditional aggregation, so we're looking at a sum or a count, there's an unbounded number of events for the entity in the window you're aggregating on. To make that concrete, if you have, say, a sum of user trades over the last 7 days, there's an unbounded number of possible trade events in that window that you need to compute. And so reading online all of those events will give you O of N online read performance, which is not acceptable for basically every use case because the latency will go up. So the approach that we use, and a lot of other presentations have touched on, is to do stateful stream computation and compaction, or you can call it tiling, so that you have a bounded number. So you basically compute chunks of aggregated tiles, and then you read a finite number of them at serving time. So that's great and really important, and we do that a lot. But one of the things interesting with sequence features, where we're really talking about a last n aggregation, possibly with an offset, is that you have a strict bound on the number of events in the window. So we explicitly set that n when we define the feature. And so compared with the traditional features, we actually know the number of rows we need to read from the online store, like the upper bound. And that allows us to do a stateless streaming model. And there's a few benefits to that. One is you get fresher features because the streaming jobs are doing even less computation. They're simply filter, transform, and write to the online store as opposed to doing in-memory aggregations. And then also generally, there's going to be cheaper streaming compute, require less resources, and also less tuning. If the event volume increases, the jobs are generally less sensitive to the increase in events and can handle it, whereas the stateful aggregations require more tuning or over-provisioning. So that's, I think, pretty interesting optimization here. And I'll talk briefly on some ongoing work. I think one pain point we feel right now is because of this work that's made it really easy to build streaming features, we have a lot more events that are being consumed by a lot more different ML applications. And it becomes a bigger challenge to manage the contracts between data producers and consumers and ensure that those events are going to be well maintained and the dependency for a given ML model, that the producer is aware of that dependency. There's a lot of foundational work we're doing with the data platform team to enforce stronger contracts. Um, and then also, I think there are some unique challenges for drift monitoring for sequence features, where like traditional things of metrics that you can apply over a numeric value are different when you're looking at an array of, say, like categorical string values. Um, the other piece is just on feature lifecycle management. In that first slide, I point out that we have now gone from like 100 to 300 roughly different streaming pipelines in the last 12 months. So making sure we have a process both to ensure that those pipelines are maintained appropriately by different client teams, and then also that as they're phased out with new versions, models upgrade to the new versions of the pipeline, and we're able to reduce costs and remove the old features. That's been an area we're investing more in. And then one other piece is Coinbase does have a mix of Flink and Spark being used in production workloads. And while a majority are now on actually Spark structured streaming and able to do sub-second freshness, we have started also moving to real-time mode, which is originally a Databricks feature, but now I do believe it's also been part of it's getting added to open source Spark. And that is a new streaming model that can give like very, very similar performance to Flink. And so we're moving to that and getting really strong. Like now we're measuring single digit millisecond end-to-end freshness. So those are some of the ongoing work. And yeah, that's my presentation. Forward to take some questions. Thanks.
Thanks a million, Joseph. Really, I'm just looking at the scale you're working at and the number of features now. It's very impressive. I guess the crypto industry is much bigger than many of us may know at this point. I have a couple of questions. There's two questions actually I can see on. But I'm going to take one first. I'll plug firstly, Tile Window Time Aggregations, Chapter 9 of my book. You can read more about them there if you're interested. No, I have a question about data contracts. You brought it up in the last one, which was, and we haven't talked about it. It came up in a few talks already. But what are the fundamental difference between data contracts for machine learning versus for data engineering? And an obvious one would be something like feature freshness, right? But what else do you see, and what do you think should be in a data contract for features?
Yeah, I think honestly, most of the pain points are really specific or kind of common to data engineering. It's not necessarily too specific to feature engineering, like things about strict schema controls and schema evolution, and also just visibility and having like really great lineage between event producers and then the maybe intermediate consumers and then the final consumer, which is usually ML. Yeah, freshness is probably we're more sensitive to that than maybe other typical data engineering pipelines. Um, Yeah, and then we also, I guess, one other piece is like now the feature is not actually the last stage in this lineage in these contracts. There's a model, and that model might also those scores might be used in another streaming pipeline. So it's actually quite like we're both like the last step in this lineage, and then we often are also a producer. And so like that full feedback loop of establishing contracts, not just to the Spark pipeline running, but also the model and downstreams is a big piece for us.
There are a couple of questions. I'll take one of them because one of them the first one we can take in Slack, but the second one is related to high traffic for sequential features over a longer window. So say 2,000 events over 30 days. What challenges do you see in your online database? I would extend this also say what are the ML frameworks, right? So you mentioned embeddings, of course, which is an obvious one because we've got variable length sequences. Are you doing transformers or LSTMs, or what are the downstream implications on sequence features for your modeling as well?
Yeah, there's a bunch on the modeling side. I know transformers and LSTMs are definitely two of the most used approaches. You can also use sequence features though as traditional features in a model. So like it's very powerful where you can also, if you just have a normal traditional like a tree-based model, you can incorporate like take the sequence and compute entropy to look at like the basically differences in events in that sequence. So we find that like even models that aren't doing something as advanced as a transformer can still make use of these features as well.
Fascinating. Thanks, Joseph. We're out of time, and there were a couple of questions. A question we can take it on Slack, and looking forward to hear more from Coinbase in the future.